Hello and welcome again to this second session of Bayesian data analysis with JASP. So in this short video, I will do a quick recap on condition probability to then get in touch with Bayesian analysis and also Bayes rule. Okay, so condition probability is one of the things that we left in the wake in the previous session. So we are going to recover it because I think it's crucial to understand with good level the Bayesian analysis. Okay, so just a quick recap from previous sessions. We got probabilities and we have operations with them. For example, the probability of something, of its complementary, the probability of the union or the intersection, and we also had the condition probability principle. That is the probability of something occurring given that something has already occurred. Okay, so the formula to do this is basically this one. So we got that the probability of A dash B is the intersection that the A and B happening at the same time divided by the probability of the second thing occurring. Okay, so this is also called condition probability or probability of A given B. And we can also deduce that therefore the intersection between the probability of both of them happen at the same time is going to be that condition probability multiplied by the probability of the second event occurring. And also we know that if the two events are completely independent, conditioning on one of them doesn't impact at all the other event. Therefore, the condition probability of A given B is going to be just the probability of A because they are independent. What happens to B has nothing to do with what happens to A and vice versa. Okay, so I really like to illustrate condition probabilities with cross tables because I think it's very visual and also very intuitive. So we just imagine this cross table that we have event 1 that can have the values 1 and 0, and event 2 that can have the values 1 and 0. Therefore, we encounter with these four combinations like 1, 1, 1, 0, 0, 1, and 0, 0, and we have the marginals here, that is all the amount of all the times that event 2 has been 1 and has been 0, and also for event 1. And we have the total amount of repetitions of a random experiment. So here are our conditioned proportions or our combined proportions by row or by column. Okay, so we can fragmentate this cross table into different probabilities following or taking into account which is our sample space. So if our sample space is the overall amount of all of the repetitions of the random experiment, therefore we got the probabilities of event 1 turning 1 or 0 and event 2 turning 1 or 0. But also these four cells turn to be intersections, like the probability of event 2 being 1 and event 1 being 1 at the same time. They are intersections. They are the two things happening at the same time. However, if we set our sample space, our universe, as only event 2 turning into the value 1, therefore these two probabilities transform into conditioned probabilities. Therefore, we got that given that event 2 is 1, this is the probability of event 1 being 1 and event 1 being 0. And we can do the same for the other row. This is the probability of event 1 given event 2 is 0, and the probability of event 1 being 0 given that the event 2 is 0. We can do the same process here by columns. Like, given that event 1 is 1, then what is the probability of event 2 being 1 or 0? Okay, so this is a very, I think it's visual and intuitive. Here's a practical example with gender identity and smoking tobacco. So we have men and women, smoker, non-smokers, and ex-smokers. So we have a sample of 150 people. So these are all of the frequencies, the raw data that we have just counting in. And then we got marginal distributions. For example, men and women. We can see that we have more men than women, 100 men and 50 women. And also we have 60 smokers, 60 non-smokers, and 30 ex-smokers. If you turn them into proportions, for example, 0.66 and 0.33, 0.40, 0.40, and 0.20, we can interpret them as the probabilities of each of these events happening. For example, the probability in our sample of being men is 0.66. So it's more likely to be men than women in our data. And also, it's more likely to be smoker or non-smoker, because they are the same number or the same probability, than to be an ex-smoker. Okay, so now we can do the same thing, but with our condition probabilities. If we condition on being men, here we have this row of values, 30, 50, 20, and 100, then these values are going to be divided by 100 to obtain new proportions. If we translate them into probabilities, are the probabilities of being smoker, given that you are a man, the probability of being a non-smoker, given that you are a man, and also the probability of being an ex-smoker, given that you are a man. So, as you can see here, there are different values that we have in the marginal distribution of smoking, and we have that is more likely, if you are a man, to be a non-smoker, because it's the highest probability of all. We can do the same for women, and you can see here that in our data, given that you are a woman, it's more likely for you to be a smoker instead of non-smoker or ex-smoker, because it's the highest probability. So we can do the same for columns, and we got this scenario where we have gender given smoking, gender given non-smoking, and gender given ex-smoking. So in smokers, we have in our data that they are basically the equal proportions, therefore equal probabilities, conditional probabilities. We also have that it's more likely to be a man given that you are a non-smoker than a woman, and also it's more likely for you to be a man than a woman given that you are an ex-smoker. Okay, so this is basically conditional probabilities in a nutshell. And also I want to illustrate this with a cautionary note on how conditional probabilities can give you very different values than marginal distributions. And if you want to describe a complex phenomenon very well, you need to take into account all of the possibilities, including the ones that you are not conditioning. For example, this recent hot topic about vaccines of COVID-19 and being hospitalized, because if you conditioned on being hospitalized, you can see that vaccinated people and unvaccinated people are kind of more likely to be vaccinated. However, if you take into account the enormous amount of people being vaccinated, this doesn't seem to be very relevant. Okay, so this is how and why you need to be careful about conditional probabilities. Okay, so nothing more on that. A quick recap.